What's up? Welcome back. In this episode, you'll learn how to solve day 12 of the Advent of Code from 2022 with Ruby. This one's called the hill climbing algorithm. So we're going to receive a map as our input. It looks like this. And the S represents where we're going to start. The E represents where we're going to end. And all of the letters on the map represent the elevation or sort of the height of the hill at that point. Now, as we're navigating and trying to find our way from S to E, we can go either up, down, left, or right from our current position, and we can explore in the direction of one of those neighbors as long as the letter or the height in that position is at most one greater than the current position. So we can go from A to B, but we can't go from B to Q because Q is too much of a jump from B. We can also go downhill. So if we're at letter C here, we could go down to B, but we could also go down more than once. We can go all the way down to A. So this is our input. So we'll grab that and we're going to drop it into a new Ruby file here. We're going to say at the end, we're going to say something like if argv.empty. So if argv is empty, we're going to say our data is data.readlines chomp true. Otherwise, if we did get an argument passed on the command line, we're going to say data is file.readlines of argv0. Now what we can say is like our grid is data.map into chars. Let's parse our input a little bit here and convert it from this grid of characters into a grid of heights that are in like as integer values. So we'll say something like grid.each with index do row, and then row.each with index do cell. And I think I want to stick with X and Y here. And if the cell's value is the S, we want to do something. If the cell's value is E, we want to do something. Otherwise, we're going to handle all of the other letters. So if the cell's value is start, then we want to mark the grid, or we want to mark a height. Let's keep track of this new thing called heights. And this will be a array.new of grid.size, grid.first.size, and then we'll just fill it with nils to start. So here we want to say heights at X and Y is going to be equal to 0. So, or let's make it equal to 1. So if we're starting from S, we want the height of S to be 1. Now if we're starting, or we're going to end at E, so E is the top of the mountain, and E is going to be adjacent to the letter Z at some point. So we're going to say heights at X and Y in this case is going to be 26. Otherwise, we're going to set the heights at X and Y to be equal to cell.ord, so the ASCII value for the letter, minus a.ord plus 1. So that should give us like 1 for A, 2 for B, 3 for C, etc. So now let's print out our heights and just see if we got something reasonable. All right, 1, 1, 2, 16, blah, blah, blah. And if we look at this, then we should have gotten, we should have gotten 1 for S, 1 for A, 2 for B, and then Q is probably 17. All right, so then second row had A, B, C. Is that right? A, B, C. Okay, so I think our heights are correct. Now what we want to do is create a way to visit all of the neighbors of each of the cells in the grid. So now we need to like iterate over each of the neighbors. Now, in order to do this, there's a couple different common algorithms. One is depth first search, another is breadth first search. We're going to use something like breadth first search, where we're going to look at all of the neighbors around us first, and then we'll keep track of some distance maybe. And then if there's a distance that's better in one case than another, then we'll go in that direction. So we'll keep track of something else called distances. And this is going to be a dictionary where the key is going to be an X and Y coordinate, and the value will be how far that is from the start. So in the case of S, distances at X and Y is going to be equal to 0 because that is the starting point. Okay. And now what we need to do is somehow iterate over all of the neighbors of each cell. So the place that we're going to start at is going to be, we'll call this neighbors, and we'll put this into an array. And so if we're encountering the starting point, which is S, then we want to add S into a list of neighbors that we want to visit and then we'll use that in our algorithm. So neighbors push in XY. Okay, so now what we're going to do is we're going to write an algorithm that says until neighbors are empty, what we're going to do is we're going to pop off. Oh gosh, look, it's already writing it for us. So we're going to pop off X and Y, and that's going to be neighbors.shift. And the reason we're using shift here instead of pop is that we want them to come off of the front of the list of neighbors in order to like look at all of the sort of layers of neighbors in order. Otherwise, if we used pop here, that would be depth first search, but we want to use shift so that we're using breadth first search. Let's worry about distance in a second. So first we want to go through like some group of coordinates. So we're going to say, if we're going to go, let's say we're going to go left, right, up, down. So this should give us right, actually right, then left, then up, then down, or down, then up. Okay. So that gives us the deltas in each of those directions. Now we want some new X and Y. Oh gosh, it's trying to like jump ahead here. Okay, so we want new X and new Y to be X plus the delta in that direction and Y plus the delta. So this new X and Y is going to be the coordinates of a new neighbor that is relative to the neighbor that we're visiting right now. Okay, so if X is between 0 and grid.size and Y is between grid.first.size, then we should be at least on the grid. Next, what we want to check is whether or not we can actually go to that position. So here we want to say something like the new height of that neighbor should be less than or equal to the heights of the current position plus 1, because we can go up at most 1, but we can go down more than 1. So this should give us, that should at least keep us on the board. Then what we need to do is add this neighbor. This seems like a valid neighbor, so we want to add it to the list. So neighbors, shovel in NX, NY. So by default, that's going to give us, that should give us all the neighbors, or it should like at least help us visit all the neighbors. But if we take this approach, then we have no way to like exit or break out. Because our graph here has cycles, we're going to end up in a cycle. So we need to keep track of where we've seen something before, and we can use that with distances. So we want something like if distances at NX and NY is nil. Okay, so is this right? So if the distances at the new position is nil, and it should be because we've never seen it before, or the distances that we've already calculated for that position is bigger than what we're going to get right now, which would be, this doesn't make any sense. Oh, wait, hold on. Okay. So distances from the current position, so this is our current position plus 1, is the distances that we've already tracked for this new X and new Y for this neighbor. Is that greater than? So like, was it the last time that we saw this option, was it more expensive to take this route than it would be to take the current route? So then we want to say something like distances of, yeah. So actually let's pop off distance, or we'll just grab distance is, the current distance is distances at XY. So then down here we can say if, yeah, then we can say distance plus 1. And I think that should terminate, right? Because if it's not nil, so if it's nil, that means we haven't seen it. If we haven't seen it, we want to add it to our list of neighbors to go check out next. And we also want to add it into the list of distances. So the very first time that we go through, recall that our distance for S is going to be 0. So this is the first time we enter this, we have S inside of our list of neighbors, and we have distances with S's position, and that's going to be equal to 0. So we get S's position, and we get 0. Then we're going to go to all of the neighbors, and as long as the neighbors are on the board and the height of that neighbor is valid, like we can actually go to the neighbor, then we're going to check, have we seen this before? And if we have seen it before, was it worse? And if it was, then we're going to add that neighbor for us to go check. And then we are also going to add 1 to the distance from S. So the first neighbor, for instance, now that distance is going to be 1. So in order to get to like this A, this is going to be distance 1, distance 1. Those two should be the only ones that are added to our distances from S because we can't go diagonally. All right, so then at the end, we should have some P distances. And let's see. Okay, so heights at NX. So there is no heights at NX. Oh, this might need to be grid size -1 and first dot size -1. Okay, so now we have a bunch of distances. Now what we need to do is like key into distances for where E is. So how do we figure out where E is? Let's just keep track of E in a variable here. And when we see E here, we'll keep track of the end position with X and Y. And so then we can just say like print out distances for E, and that should give us an answer. So 31. Okay. So 31 is the answer for the test case. So if we grab all of our input here and open up day 12 input, paste all of that in, and open up. Okay, so then we've already got this argv stuff at the top, so now we should be able to say Ruby day 12, Ruby or day 12 input. And when we execute that, we get back the number 350, which is the puzzle answer for part 1. Okay, let's talk about part 2. So in part 2, we want to figure out the most scenic route, not just the route that starts at S. So to maximize our exercise while hiking, we want to start at any of the A's basically. So any square at elevation A is going to be a valid path, and we want to find all of the shortest paths from any A to E. So I think at this point we need to just like figure out where all of the A's are. So the big difference here is that instead of just adding S's in here, we also want to add E or A's in here. So or cell is equal to A, then that should give us all of the stuff starting from A. And we get 349. It's a little bit different than 350. And that was our answer, our puzzle answer for part 2. So that is part 2. Okay, so it actually took me a little while to figure this out. And I went down a path of trying to create nodes. And I also went down a path of accidentally not shifting. I was popping. And so there's definitely like a lot to this algorithm and getting it right in order to match the answer. But hopefully this was useful. There's a couple of different tricks in here, like iterating over the deltas and then applying those so that you get back some new deltas. That's like a common thing. Using the between method to check if something is between some number and some other number. That might be new. And then what else is interesting here? There's a couple little things we could probably do to clean stuff up, but I think that's pretty good. So we'll leave it there. Thanks again so much for watching, and we'll see you in the next one.